Dear students, next topic we'll discuss how the resistors, the value of the resistance depends upon the temperature. If you increase the temperature of a conductor or semiconductor or any alloy, how their resistance would be affected. So our topic is temperature dependence of resistance. Temperature dependence of resistance. Resistance or resistivity, whatever. Basically, resistivity of the material will be dependent upon the temperature. So, how the temperature is going to affect the resistivity of any material, that we are going to see here in this case. In case of conductors that we have seen, in case of conductors, the resistivity of the material will get increased if we are increasing the temperature, because the relaxation time will get decreased, means more number of collisions are going to take place, and the randomness of the electrons will get increased, and hence the resistivity of the material will be increased. And in case of semiconductors, if you increase the temperature, already the charge carriers are very less, so the conductivity is very less. But when we increasing the temperature, then what would happen? The charge carriers which can conduct the electricity will get increased, and hence the conductivity will get increased and the resistivity will be decreased. So in this particular topic, we'll see for limited range of the temperature how the resistivity of the conductors or alloys is going to be affected or changed. So I'm writing the direct formula here. The resistivity of the conductor at any temperature is equal to resistivity at reference temperature. Reference temperature may be the room temperature, or that is any reference temperature or the set temperature. It is 1 plus alpha delta T. This is the resistivity at the temperature T, that is the desired temperature. This is the resistivity of the material at reference temperature. Alpha is the temperature coefficient of resistivity. And delta T is what? Delta T is change in temperature. So using this formula, we can find out the resistivity of the material at any temperature. So how we can define this temperature coefficient of resistivity, alpha? From this equation, we can write what is the value of alpha. Alpha delta T can be written as rho T over rho naught. 1 plus, and this 1 will come this side, it will become minus 1, and this can be written as rho T minus rho naught divided by rho naught. So alpha, this delta T will come here. So this is the formula for the temperature coefficient of resistivity, that is alpha. And what is the unit of alpha? Unit of alpha is, you can see, this is resistivity, this is also resistivity. So this is per Kelvin or per degree centigrade or Celsius. So the unit of this temperature coefficient of resistivity is inverse of the temperature. So this alpha, for finding the temperature dependence, means how the resistance of the materials depends upon the temperature. So this alpha plays a very important role. As we have discussed in case of conductors, the resistivity will get increased. What we can say? the resistivity at higher temperature. For example, we are increasing the temperature. For example, suppose we are increasing the temperature, means initially the temperature is less, finally the temperature is more. So we can write delta T is positive if we are increasing the temperature, and this is positive. If we are increasing the temperature, the resistivity is also getting increased in case of conductors. So we are talking about conductors. In case of conductors, when you are increasing the temperature, resistivity will also increase. So what we can write, initial value of resistivity is less, final value of the resistivity is more. So this will become positive. This is already positive. So change in resistivity is also positive. So for the conductors, what we can say, alpha is positive. In case of conductors, the value of alpha is positive. And what about in semiconductors? In case of semiconductors, I am writing here, for semiconductors, we are increasing the temperature. Suppose we are increasing the temperature, so delta T would be, delta T is positive. But you see, when we are increasing the temperature, conductivity will get increased because of more number of charge carriers, and resistivity will get decreased. So what we can write in case of semiconductor, this resistivity at the higher temperature would be less than the resistivity of the initial temperature, at initial temperature. So this term would become negative. So what we can write, delta, resistivity at temperature T minus rho naught is less than 0, or we can say this is negative. So this is negative, this is positive. So alpha is what? Alpha is negative for semiconductors. So higher value for conductors, a positive value, and for semiconductor it is negative. So if let me draw some graphs. This was the case of resistivity. If the resistance is given, if resistance is also given, then also you can use the same formula. What you have to do, L over A, L over A. What you will get? Rho times L over A is the resistance. So same formula can be used for the resistance also. Means resistance at temperature T is equal to resistance at reference temperature 1 plus alpha delta T. The same formula can be used to find the resistance as well as resistivity. So this alpha is again the same temperature coefficient, and this is a higher value of the resistance. For in case of conductors, this is reference temperature's resistance, and delta T is the change in the temperature. Now let us draw the graphical representation of some of the materials. First, I am drawing for the copper. Copper is a conductor or metal. 0, 50, 100. This is the temperature. And this side I am taking resistivity. And I am taking 10 raised to minus 8, as copper is very good conductor of electricity. Ohm, centimeter, ohm meter. And here temperature we are taking in kelvins. And the graph for this limited range, there is much increase in the value of the resistivity. You can see here for the small variation from 50 degree to 150 degree Kelvin, there is much increase in the resistivity of copper. But if I draw the graph for any alloy, as we have already discussed, alloys are the materials which are basically insensitive to the variations in the temperatures. Their resistivity is remaining approximately constant. So small variations, the resistivity of alloys will remain constant. So alloys generally, we use alloys for making the resistance coils. These are nichrome, manganese and constantan. So here Again I'm taking the resistivity in micro ohm meter, and here I'm taking 200, 400, 600, 800. So this side I am taking temperature in Kelvin, and this side I am taking resistivity. And here the values are approximately 0.2, 0.4. And this side I am taking the value 1, 1.10, 1.1, 1.10, 1.20. And here in this large variations of the temperature I am going to draw. So this was the graph for copper, and the second graph I am going to draw for the material nichrome, which is an alloy. And the graph is, you will see that there is not much change in the resistivity of the material, and for this large variations in the temperature, the graph is like this. If the temperature is going to increase from 200 to 800, there is not much change in the value of the resistivity. And one third more graph we are going to draw for the semiconductors. And we know that in case of semiconductors, the resistivity will decrease if you are increasing the temperature. Resistivity, why the resistivity decreases? Because charge carriers are going to get increased. Now let us draw third graph for semiconductors. Resistivity this side, and this side I am taking temperature, so I am just drawing the shape of the graph. Semiconductor, the graph is like this. So if we are increasing the temperature, the resistivity will get decreased. Now the same thing we can explain with the help of the formula. The formula of the resistivity, we know that that formula we have already derived. It is m over Ne square tau. The resistivity is m over Ne square tau. So using this formula we can explain these graphs. For conductors, you see N is the number density of the charge carriers. In case of conductors, already if the temperature is low, conductors, we know that there are large number of free carriers. Already abundance of the free carriers are there. Free carriers are here, electrons. Free electrons, they already exist. So small variation in temperature are not going to affect too much this number. But basically this tau is going to get affected. So if this tau, if you are increasing the temperature, more collisions are there, and relaxation time will get decreased and resistivity will get increased. But in this particular case, N is increased and resistivity will decrease. Collisions, because the charge carriers are very less in case of semiconductors. Very few charge carriers are present. Charge carriers may be electrons and holes in case of semiconductors. But when we are increasing the temperature, the number density, this is increased. So number of free electrons or free holes, they will get increased and the resistivity will get decreased. So this is all about the temperature dependence of the resistance or resistivity. So you can ask questions, which materials can be used to make the resistance coils. Nichrome can be used, manganese or Constantine. Why? Because their temperature coefficient is less, alpha is less. What is alpha? Alpha, we know that this is change in resistivity over original resistivity into delta T. If there is large change in the temperature, this is not too much change. There is not much variation in the resistivity. So we can write here alpha is less for these materials. So that is why we use alloys to make the standard resistance coils, and this material is also used for making the potentiometer wires, because we want that if we are using any resistance coil, its resistance should remain constant for one particular experiment. Or if the resistance is remaining constant and you see if the continuously current is flowing through the coil, its temperature is automatically going to get increased because of the heating effect of the current. So just by the increase of the temperature in itself, if its value is going to get increased, then we will not get the accurate observations, means the resistance coil itself is not constant. So other values of the resistance or other parameters of the experiment, they will not be accurate if we are not using this material. So these materials are used, at least our resistance coil, if it is of 1 ohm, its resistance should remain 1 ohm for one experiment. So it should not change. So that is why we use these materials, alloys, for making standard resistance coils.